happening?
Her service assignment is submarine warfare. Before she starts that, in the fall, she will be attending Oxford University to pursue not one, but two master's programs, one in mathematical and theoretical physics, and the other in energy systems as a Bayer scholar. Daisy was a plebe in my plebe chemistry class, and she's come a long way, but I knew the spark in her when she was a plebe, and I'm so proud that she's being a Trident and doing her research now.
Thank you, Dr. Schroeder. Thank you. Thank you, Dr. Schroeder, for the very warm introduction. It's so nice for us to have come full circle, so I really appreciate this moment. Good afternoon, everybody. My name is Midshipman First Class Daisy Zamora. Thank you all for joining me for my Trident Scholar presentation. My research focuses on zooming in on dual and binary supermassive black holes with the James Webb Space Telescope using a technique called aperture masking interferometry. I'll say just a little bit about this project and how it got started. I've been working on this project for some time, since plebe year, actually. So this project started when I thought it would be fun to study black holes and combine that with AMI. So that being said, our primary objective is to create models of dual and binary supermassive black hole systems using aperture masking interferometry in order to determine the feasibility of a real-world observation using the James Webb Space Telescope. So let's start off with some background. I think that would be very useful in the context of this presentation. We start off by defining a supermassive black hole, which is comprised of three main components, the first of which is the accretion disk. The accretion disk is comprised of all of the matter orbiting past the second component, which is the event horizon. The event horizon is this dark circular region past which matter needs to be traveling faster than the speed of light in order to escape the event horizon. As we know, it's not theoretically possible to travel faster than the speed of light, so this is where the term black hole comes from. At the center of this event horizon is a third component, which is the singularity. The singularity is a very small point where the force of gravity compresses matter so violently that it is condensed to a point infinitely small and infinitely dense. You can see that in this photo there are two supermassive black hole systems undergoing a merging process. It's also important to understand that supermassive black holes reside at the center of galaxies. So we can further define them in two sub-definitions: dual and binary supermassive black holes. Dual and binary supermassive black holes differ by both angular separation, meaning the distance between the two, and the presence of gravitational attraction. When supermassive black holes merge, they first begin as a dual system where they are very far apart from one another and have no gravitational attraction. As the merging process continues, they then become binary, where the distance between the two nuclei are very small and the presence of gravity attracts one black hole to the other. The distance at which gravity begins to play an influence is also known as the radius of gravitational influence. Now here's our problem statement. If I wanted to understand the way that supermassive black holes merge and therefore galaxies form, how can I do that if I'm not properly able to image the system? If I can't image it, it's difficult for me to understand it. You can see here depicted are two main sources in the north and south poles of the image, and it's difficult for me to see any fine detail within this image because of the limitations of the telescope. When we talk about limitations of a telescope, we must also discuss angular separation and angular resolution. Angular separation is defined as the angular distance between two main sources. You can see on the right and left-hand side, the two sources depicted don't differ in distance relative to one another. However, they do differ in distance relative to Earth. The angular separation, denoted θ1 on your left-hand side, is much larger than that on your right-hand side. Now, this is a problem when we discuss the angular resolution limit of a telescope. The angular resolution limit is the ability of a telescope to distinguish small details of an object being imaged. So here's the problem. If the angular separation of a system is smaller than the angular resolution of a telescope, we're not able to define those fine details, which means that I can't then understand it, which means then how can I understand the merging of galaxies? We propose using a technique called aperture masking interferometry, or AMI. AMI builds off of the double slit experiment, which many of us are familiar with, hopefully from physics. The double slit experiment has 4 primary steps. The first is the source emitting light towards the two slits depicted on the left-hand side there. There is then a barrier behind those slits which captures the interference pattern. That interference pattern is able to give us information regarding the separation between the two sources and the distance of the two sources and other similar spatial information. AMI again builds off of this principle to not only do a one-dimensional analysis, but now 2 dimensions. AMI, for our experiment, we wish to implement it on a space-based telescope, in our case, the James Webb. Now, we've progressed again from the double slit experiment to the non-redundant mask depicted here at the center. Instead of 2 slits, we have 7 holes, 7 sub-apertures. The sub-apertures will shunt about 85% of the incoming light from the source. It may seem counterintuitive to only allow 15% of the light. Why would we want to do that? But what we actually find is when we do shunt that light, we're able to distinguish a finer detail from our incoming source. So how did we do this? I'd like to just start off by pointing it was a very extensive process. The most difficult thing about doing something people haven't done before is doing something someone hasn't done before. So it took a lot of trial and error, a lot of modeling. We begin by sorting through the Big Mac catalog. This catalog is a catalog of thousands of sources, which is dynamic list. It is continuously updated. It includes dual sources, binary sources, other kinds of supermassive black hole systems at different redshifts, at different angular separation, captured through a variety of telescopes, both Earth and space-based telescopes. As you can imagine, this would have been a very extensive process to do one by one. So we utilized a tool called TopCat, which is a software tool that allows us to filter quickly through a large list of astronomical data. When we did filter through this list, we used 4 main parameters. The first, of course, would be the source classification. We wanted to primarily focus on dual and binary systems. The second is the confidence level. The Big Mac catalog sorts sources on a scale from -1 to 1 in half-step increments to determine whether or not a source is -1, unconfirmed to be a dual or binary candidate, or +1, confirmed to be a dual or binary candidate. For our sake, we wanted to focus on a confidence range of 0 and 0.5 because we wanted to leave room for discovery. We didn't want to be told the answer. Our third parameter that we filtered is known redshift. We can think of redshift as the distance that a source has from Earth. For our experiment, we wanted to focus on a redshift lower than 1, meaning closer to us in space. Once we get into higher redshifts, things like 2, 3, 4, those are deep, deep space objects, and we start to introduce other confounding variables. Most importantly, we've filtered the angular separation of the two systems. AMI is most useful when looking at very small angular separations between 65 and 200 milliarc seconds. What this also allows us to do when we define that very small angular separation, it allows us to focus on the late stages of galaxy mergers and galaxy formations. Plotted here is every point in the Big Mac catalog. You can see it's very, very extensive. And at the bottom, you see the sources that we have found. We ultimately found 15 sources. On the x-axis, you see redshift. For our sake, we wanted to focus on less than 1. And we also have linear separation plotted on the y-axis. What's interesting about this plot is that you may expect that the redshift and linear separation have a linear correlation. But we don't see that. We see an increase and then a plateau. This is due to the curvature of space-time and the This is due to the curvature of space-time and the expansion rate of the universe. So again, to minimize those variables, we focus at a redshift of lower than 1. These are our 15 candidates. You can see primarily dual candidates. Our confidence region is defined as previously stated. We also have some redshift greater than 1 with a large focus at a redshift of less than 1. And the right ascension and declination correlate to their position in space. Our next step was utilizing the exposure time calculator. The exposure time calculator, or ETC, is an online interface which allows us to create models primarily, and additionally important, allows us to see what the James Webb would see if it was directly pointed at those models that we have created. This is what the ETC looks like when we're making a model. We have plotted the first 3 scenes from the Big Mac catalog on your left-hand side, and each one of these scenes is comprised of 4 main components. The first scene, highlighted in the center column, is the J0216 tag 0105. This is the excerpt from the Big Mac catalog. Source 2 is the galaxy component, which is the larger amount of matter comprising of the galaxy. And the third and fourth component is the binary component. This is what makes the system a dual or binary. We don't know, because of the angular resolution of the telescope, we don't know what the system actually looks like. That's why we need to put together as many models as possible with many varying parameters to establish those left and right lateral limits. These are the first 3 models that we have previously explained. On your left-hand side is the tag 0105 model with a brightness magnitude of 16.10 Vega magnitudes. On your right-hand side is the 6218 model with 18.26 brightness magnitudes. So even though the number is increasing, the figure on the right-hand side, scene 3, actually has a dimmer state. It is dimmer than the one on your left-hand side. I previously mentioned that the ETC is also able to tell us what it will see if it was pointed at these systems. This is what James Webb would see. You can see for the brighter scene, it's pretty feasible to observe the two candidates with the naked eye. However, on the right-hand side, it's more difficult to do so. Now, what this does not mean is that we're unable to reconstruct that original image. What it does mean is that we're going to have to go through additional modeling parameters to be able to reconstruct. In typical Naval Academy fashion, we chose the hardest thing to do, so we focused on the scene on the right-hand side. How can we put together the original model? We used a tool called LitPro to undergo a process called deconvolution. Deconvolution is the process of taking that excerpt from the JWST, what the JWST would see, and recreating that original model. When we do use LitPro, we do introduce different kinds of noise, including photon phase and detector readout noise, all of which must be accounted for in our models. So what did we see? What did we learn? What were the results? As previously stated, we focus on the most faint system from the previously 3 observed and modeled, J0854 plus 6218. This is a reminder of what JWST would see under realistic observations. We not only chose this model to focus on because it was not feasible to detect with the naked eye, but additionally because it had ideal redshift parameters of significantly less than 1 as a very small angular separation and an unknown confidence range of 0. We used the exposure time calculator to create 45 models, all of which varied in orientation, separation, and brightness. This is the first result from the ETC. This is the creation of our input models before we are given the output. You can see that the central source is kept at a 0, 0 constant magnitude, and the accompanying source will move closer and at different separations from the central source. You may also notice that there is a 45-degree angle adopted for the companion source. Our reason for including this angle is because it is very unlikely in real-world observations to see 2 sources perfectly aligned with 0 degrees offset or 90-degree offset, so we chose something nice in the middle. This is what the exposure time calculator would see if it was pointed at the systems on the left-hand side. Then the challenge becomes, can we use the right-hand side, what JWST would see, to recreate the models on the left-hand side? Again, we used LitPro to undergo this deconvolution process, and this is what it showed us. These are the reconstructed images from the original supermassive black hole system after deconvolution with LitPro. What we're looking at here is the central source plotted with a constant 0, 0 orientation, and the second red dot that you see is the companion source. They are separated with 60, 120, and 240 milliarc second separations. The yellow star represents where we would expect the companion source to be. It's interesting that we note at 120 and 240, the source and the model seem very consistent. However, at 60 milliarc second separation, we started to introduce some error. What I would like to say about the 60 milliarc second resolution is that we are now below the angular resolution limit of the James Webb Space Telescope. So although the models are not perfect, we see that this bottom panel, there is some separation between the red and the expected, or some brightness error as well. We have proven that it is possible to, in fact, use AMI on the James Webb to help define those small systems. For these models, the central source is kept at 18.26, as previously found on the Big Mac catalog, and the secondary companion is at a constant 21.2 Vega magnitudes. So we would also expect a constant magnitude for the companion source, and both sources, for that matter. To better understand the context of our results, we're going to take a deep dive for the 240 milliarc second separation. This is a zoomed up image of the output of LitPro. And this table, table 2, highlights what the best fit parameters were using LitPro. You can see that the X4 and Y4 at roughly 30 and 270 milliarc seconds correlate to the companion source. Even though this is not perfectly 0 and 240 milliarc second separation, the net difference is still 240 milliarc seconds, so we would consider this a proper fit for our input parameters. Now you may say, Daisy, Ms. Zamora, why do we still see some misalignment in the models? This is because of the exclusion of the galaxy component. We really wanted to focus on the orientation and separation before we introduced new input parameters and new models. We now move to the secondary method of confirming our models. This is a visibility squared plot. On the x-axis, we have spatial frequency. On the y-axis, we have visibility squared. If we were looking at a point source, meaning a very single point of light in the sky, we would expect a visibility squared of 1. However, you can see that we are far below that. This is because we are, of course, looking at a binary source, a binary supermassive black hole system. What the red lines are, that is the data from the exposure time calculator, and the blue points overplotted, that is the model. You can see that they are very well aligned, indicating a proper fit between our model and the given data. We move to the 0 and 60 milliarc second separation. Here again, we are below the angular resolution limit of the James Webb, and we start to visibly see some error as well. You can see that the secondary companion is not only misaligned, but it also is much brighter than expected. Although it would be very easy to say this is not a good fit, we would argue that it is an incomplete model, largely because we would still like to introduce the presence of the galaxy component to help alleviate some of that miscommunication or misunderstanding between the brightness and orientation of this model. But again, it is still possible just to distinguish two sources below the angular resolution limit of the James Webb. Here is a characterization of why the model and the data are misaligned. You can see that at smaller spatial frequencies, there is proper alignment between the model and the data. However, as we get to higher spatial frequencies, we start to introduce some error as well. So what did we learn? What were our key findings, ultimate results? Well, firstly, we did find 15 Big Mac candidates that fit our modeling parameters out of the thousands, so win. We also created 45 lit pro models of the system J0854 plus 6218 that varied in separation, orientation, and brightness. And even though the 60 milliarc second images were degraded, we did again solidify the fact that it is possible to use this imaging technique to study the late stages of merger. But of course, we don't settle for what we have now. We want to keep improving. So future work would include expanding the model library beyond 45 models. This would ideally include replacing the exposure time calculator as the primary modeling tool. The reasoning behind this is that the exposure time calculator is very labor intensive. Each model must be created one by one, and it takes a long time. The second step we would like to take is to revisit the Big Mac catalog. As I mentioned previously, it's a dynamic list, and we would like to have the most complete set of candidates. The third step is to find a way to include the galaxy components in Lit Pro. We would like to further expand on this and introduce O-imaging, which is another software imaging tool that would help us identify those fine details and perhaps increase our visibility of those fine details after the modeling process. And last but certainly not least, we would like to submit a proposal for time on James Webb Space Telescope to determine with real-world observations that our models are in fact correct. Thank you all very much. Sir? So AMI is a more complex version of the double slit experiment where instead of 2 slits, there's 7 holes, and those 7 holes are part of the mass that are on the James Webb Space Telescope that can be utilized on that telescope. Yeah, so what I will say about interferometry is this is a fun fact. The first image of a black hole, the M87, was used with VLBI, which is another version of interferometry. So AMI in space may have a variety of candidate systems. However, interferometry as a whole, it can be implemented in a number of ways to select the best modeling parameters. Sorry. Yes, yes. So, as I previously mentioned, I started research the second week of my plebe year. I was so excited. And I started off using aperture masking interferometry to study a protoplanet in the accretion disk of a star. And I was going to name it GNVA 26, but then I got told no. So, so it can be applied on a number of things, not just black holes. Yes, sir.
So I know you plan to continue your research further also. How do you plan to apply your findings in your future work moving forward with this project?
So a lot of this research is on imaging, and I have a large background in imaging, and I'm so grateful for the experiences I've had. My goal has always been to move more to the theoretical side, so I'm excited to transform this project into something more. Hopefully general relativity is up my alley. That's where I plan to go. Yes, sir. That percentage comes from the prefix cut holes on the non-redundant mask. I actually have a graphic that'll help illustrate that, sir, if you're interested after. Yeah. I suppose the range would come from which tools on the James Webb you choose to utilize. So at a full aperture, you're taking in all of the light, that's 100%. How much detail can you define with that? Whereas there are different tools and instruments that you can use to then get down to the 15%. So the range would come within those regions. Yes, sir. I got him queued up, sir.
Oh, okay. I think it was 10. Oh, never mind.
From the 28th company. Service lieutenant is Marine Brown, but he's planning this fall to attend Boston College Carroll School of Management and Finance.
All right, thank you, ma'am. All right, sweet. All right, kick off my project on physical adversity and the development of human capital. So I'm going to go over a little bit about the motivation behind the project. I'm going to get into the data sets that I use, talk a little bit about the economics identification strategies we use to find the causal effect, and then we'll talk about the results, and then ultimately conclude it up, get you guys out of here before class. All right, so first I want to talk a little about the philosophy of failure. We always tell a story at the Naval Academy that we're not only expected to fail, we're honestly encouraged to fail, with the idea that we take the lessons learned from our failures and apply it to future semesters. And you can think of a variety of people for that, like a Naval Academy example being John McCain, finished bottom third of the class and then went on to become the senator of Arizona and then ultimately the 2008 Republican nominee for the presidency. And a more famous example that we all know about is the Michael Jordan example, right? He got cut from his high school basketball team and then NCAA championship later, along with 6 NBA championships. He's known to be one of the greatest, if not the greatest basketball player of all time. And here's an example of it in the 1997 Nike commercial titled Failure. He attributes his success in his career due to how much he's failed throughout his life. Right, so for the economics question we're trying to answer here is, what are the impacts of failure on human capital formation? Right, that's going to be like non-cognitive skills, soft skills, grit, resilience, time management, and how does that affect them in labor market outcomes? Labor market outcomes with the Naval Academy application is Navy and Marine Corps results. So the research question is, how is experiencing physical adversity through failure of the PRT at the Naval Academy impacting the student's academic performance and then ultimately the military career? All right, so just a quick literature review, some of the stuff that's relevant for this project. The first one's a paper by James Heckman in 2013 showing that non-cognitive skills are malleable. That means we can create them and they affect long life outcomes. And then this is a very famous paper. If you talk to the superintendent at all, he mentions Angelina Duckworth very frequently, and especially the adjective of grit, and it's a very important predictor of success in the future, so we want to make sure we develop that in our naval officers. And the third one's adversity as a catalyst. This is application of the later identification strategy I'm going to be talking about. They use a similar approach using weather causing a shock on Ethiopian youth, which causes non-cognitive skill growth in their adulthood. And this one just talks about how the service academies are a very ideal place for economics research and just general social science research due to the mass amounts of data they collect on us. And now surveys I finished in the last couple of weeks is an example of that. And it's also a lot of it's randomized. Like we get randomly assigned to companies, making it very ideal for social science research. And the second one's a paper by my research advisor showing the trade-off between academics and sports, showing that this is a relevant topic that we are currently researching at the Naval Academy and driving how we shape the development of future officers. So everyone knows this for the most part, but for people who don't, like if you get separated from the Naval Academy and you have to pay up to $250,000 worth of tuition if you fail the PRT enough times and you get kicked out. But after the failure of like 1 or 2 PRTs, you attend the brigade training team remedial workouts, which is a workout that occurs between 5:30 and 6:30 in the morning. And that's the way we're going to define physical adversity for this project, is failing the PRT and attending these remedial workouts because they act as an additional time constraint and you have that psychological effect of feeling like a failure. Right, so these are just a possible mechanisms of failure. So when you fail, you can have the learning by doing approach, and this is kind of like what we talk about at the Naval Academy. It's like you fail, it has a negative short-run impact, but in future semesters, it has a positive outcome. And the second one is just a simple crowding out effect. That's just a short-run decrease in your performance just because you have less time allocated to studying. And the third one's a self-fulfilling prophecy. This was like you're already acting suboptimally, and then that failure just amplifies that inefficiency, and you get even worse off than you were before. But the overall end state of this project is to provide an empirical estimation of the net effect of failure on academics. Right, so moving on to the data sets. I use 3 primary data sets. The first one being the PRT, which has about 190,000 observations occurring from 1999 to 2020. Then we got the midshipman academic stuff. This is including admissions data and then everything that occurs at the Naval Academy. And I use a third data set for one of my identification strategies about BWI weather. And the way we did this was we cleaned all the PRT and midshipman academic data sets to standardize them for summer exams because we don't know where to apply their academic information to, either the spring or the fall, so we just got rid of them. Anybody who validated the PRT, because it duplicates their results, so one person runs the max time in the fall, that exact same score gets added to the spring, but that exam doesn't occur in the spring, so it's not proper data, so it's inflating our results. And then we got rid of students with A+ semesters. These are people who are delayed graduates, went on Mormon missionary, left for medical reasons. We didn't know what to do with their academics, so we got rid of them. Then we integrated them all into the PRT data set with the weather and academics, and then each unit of observation of these data sets is a student running the PRT on a given day. Right, here's just some descriptive statistics of the data sets, so like a little bit of the average keeper between 1999 and 2020. But I think the key point of this data set is the PRT run failure. It's about 3% of midshipmen of all the observations failed PRT, which corresponds to about 5,226 exams. So it's a pretty limited number relative to the 156,000 observations that we have total. Right, so moving on to our identification strategies, we use 3 primary identification strategies. The first being OLS, that's what we usually associate with correlation. And then regression discontinuity design and a variation of it called donut RDD. And then the 2-stage least squared. So for OLS, this is the typical thing when you hear correlation, not causation. This is what we're talking about. We're just trying to see how 2 things move with each other, and that's with the PRT failures in academics. We're just trying to estimate the beta 1 coefficient to find that correlation. Right, the reason why OLS is invalid is because of endogeneity, and this is when unobserved factors affect both physical and academic performance. So an example of this could be mental health. If you have a mental health crisis during a semester, you're probably going to fail the PRT, and you're probably going to have a lower academic performance. But because OLS can't distinguish between the effect of mental health on academic keeper and PRT on academic keeper, PRT failure is going to absorb that effect of mental health, which is causing a biased result. Because of this, we adopt a more sophisticated identification strategy for economics. We do a regression discontinuity design where we exploit the cutoff of PRT failure and compare those who barely pass to those who barely fail, because they are fundamentally the same in terms of observable and unobservable characteristics. So here's an example. We've got the standard RDD. We have the PRT failure cutoff. Everyone to the left pass, everyone to the right fails. And that's going to be the 10:30 and 12:45 failure times for men and women respectively. But because the people on the far left, the people who max the PRT, are fundamentally different than those who fail greatly, we don't want to include them in our identification strategy and the estimation of the causal impact of failure because they're different. Because people who max the PRT are just fundamentally different than those who don't fail the PRT. However, we do have some concerns with the standard RDD regression because midshipmen can exert enough effort to avoid failure, despite that not being reflective of their actual underlying characteristics. This is the people I like to call the max relaxers. They should be performing well above the RT failure cutoff, but they're getting grouped in with the people who are genuinely barely passing, and that's causing bias in our estimates because the people to the left side of the failure cutoff are fundamentally different from the people on the right side of the failure cutoff now, which is going to cause bias in our estimate. And here we can see a visual test of it. You can see by the red line and the gap between that and the blue line, it shows that there is a jump right before the failure cutoff, and there's a major drop-off after the failure cutoff, showing that midshipmen are clumping and manipulating the runtime to avoid the treatment effect. Right, so the way we address this is through a donut RDD, and we're going to do the same thing where we apply an optical window on the outside, but we're just going to remove the results immediately following the cutoff where the clumping is occurring. And this is a histogram of the centered runtime, so this includes both males and females, and is showing the runtime relative to the failure. So 0 is the failure time, everything to the right is over the runtime, causing you to receive the treatment of BTT and experience that adversity, and then people to the left are not experiencing that. That's going to be our control group. Right, so here's a very exaggerated example of clumping. You see right before the PRT failure cutoff, there's a lot of people manipulating the runtime just to avoid the treatment and exert the bare minimum effort. And that's going to cause us to group in like some of those people who should be more associated with the maxers into the people who are barely passing and barely failing. So what we're going to do is we're just going to get rid of those results, and then we're going to do the exact same thing in the standard regression discontinuity and exclude the people who are maxing and failing greatly because those people are fundamentally different. So it looks like a donut, hence the name. Right, and our third identification strategy is the instrumental variables. We're using IVs to predict whether or not a person will fail the PRT because it's correlated with our error term. Because PRT failure is correlated with the error term, and that's going to be like the grit, resilience, natural underlying ability. We have to use an instrument with no relationship, but no relationship with the outcome variable, but does affect whether or not a person fails the PRT. The most obvious example would be like weather. Like picture running on a day that's 95 degrees and a day that's 10 degrees. You're going to either have a heat stroke or your legs are going to cramp before you run like a really good time. But that exogenous effect that's outside of the experiment, it causes a person to fail the PRT, which is unrelated to some of those unobservable characteristics. Right, so the two instruments that I use is weather. So we got the temperature, heat index, wind chill. That's pretty intuitive. But then the second one we use is called the lambda leave one out estimate, which is just the average runtime of your peers in a company class year. So if I was in 28th company and I was a first class, I would calculate the average runtime of everyone besides myself. And that's going to be very predictive of whether or not my runtime is going to be, it's just very predictive of my runtime because my peers run worse, I'm probably going to run worse. So we use those predictive values in our first stage to predict if someone will fail. Then we use that predictive value of failure to find the causal impact of academics Cooper. Right, so here's just weather correlation plot. Just shows that weather matters in whether or not for a person's runtime. And it's just a bin scatter plot taking the average of each bin, a little bit more visually appealing representation. Right, so getting into the results of it. So I first want to show the improper OLS regression, which is just showing the correlative impact of PRT failure on academics, which is non-causal. This is with the overinflated and improper way of doing things, but shows why we need more sophisticated identification strategy to find the causal impact. So we see on average when midshipman fails the PRT, we predict that they will have a 0.435 drop in your academic Cooper, which corresponds to about half a letter grade to a full letter grade. So that's pretty significant. But once we apply fixed effects and absorb some of the other variations, like natural ability, SAT scores, like anything that could matter in whether or not a student is a good student, it drops all the way down to 0.082. And that kind of shows why we need a more sophisticated identification strategy. So this is the standard regression discontinuity results with clumping. So this is also biased because we're grouping in those people who are fundamentally different than those who are barely passing and barely failing. And we see that the effect drops to 0.130. So on average, we predict when a midshipman fails the PRD, they will experience a 0.13 drop in their academic Cooper, and that's statistically significant to the 1% level. And once we apply fixed effects, it drops down to 0.093. Here's a visual representation of the donut regression discontinuity results. We're looking at people on the left side and the right side and seeing how the effect jumps at the failure cutoff. And we can see on the left side, people who don't receive the treatment of BTT, there's a significant jump from the people who do fail the PRT. And we find that the causal effect here is a 0.151 drop in academic Coopers, statistically significant at the 1% level on average, all is equal. But we also looked a little bit more into it because we're talking about, it ties back to the motivation, we're talking about the Michael Jordan. We want to find the Michael Jordans of the Naval Academy, and we're estimating the average effect of failure. So if we look at the t equals 0 on the x-axis, that's the time relative to failure, and on the y-axis, that is our point estimates of the effect on academic Cooper. So we see in t equals 0, that's when we fail the PRT. We should expect a decrease in academic performance when you're attending remediation and you failed the PRT, but the idea being that you carry it on to future semesters and it has a positive impact. But we see here that we have actually a negative impact even past the day of failure and after we are no longer required to go to BTT. So here's an example of the Michael Jordan effect. We would expect the results to be up there if the midshipmen experienced grit and became better because of it, but we don't see that. We see that midshipmen are negative overall. But this is also the average effect. Like, not the average midshipman is like Michael Jordan. Right. Now you can laugh, it's fine. So for first stage result, now we're moving on to the identification strategy for two-stage least squared. This one's just showing that weather matters in predicting whether or not a person fails the PRT. So we have two sets of instruments here. We use the base set, which is just using the average runtime of your peers in a given company on a class year on an exam day. And then we have another one that incorporates temperature and heat index / wind chill at 0800, because that's pretty much the average time a person will run the PRT for the brigade. And then in the two-stage least squared estimates, we find that the causal effect of failing the PRT under the instrument set that uses the average runtime to be a 0.255 drop in academic Cooper, only statistically significant at the 10% level. But when we incorporate those weather instruments, we find that the causal effect of failing the PRT is 0.265 on average, all else equal. Right, so to wrap this all up, so under the RDD framework, we had that 0.151 drop, statistically significant at the 1% level, using that donut approach. And then when we do the two-stage least squared, it jumps from 0.151 to 0.255 and 0.265 academic Cooper drop on average, all else equal. So we're still trying to identify that subgroup of midshipmen that experiences the development of grit and non-cognitive skills. So that's the Michael Jordan effect we're talking about, because we're just showing the average effect. So we're trying to find like somebody like prior enlisted or people select military or marine ground or people with high SAT scores, low SAT scores, high BMI, low BMI. Someone is going to respond differently to grit, and that's going to be our example of Michael Jordan, John McCain, Jimmy Carter, you name it. But once we identify that subgroup, the exact same methodology can be applied to the long-run outcomes, such as there's a fourth data set that we haven't used yet, but it ties midshipmen's performance at the Naval Academy to their future officership. So it's going to have their fit reps, their promotion rates, time in service, all that stuff that we can measure the effect of PRT failure here on long-run outcomes. Right, so there's some policy implications with this research. If you ever talk to the superintendent, he says this quite a bit, but is the juice worth the squeeze? And what he's trying to say there is, say, PRT failure is crowding out academic performance, so are we acting optimally? And for a short-term impact, like, hey, we failed the PRT now, we're having a lower academic performance because of it, are we acting optimally with doing 530 BTT workouts, or is there another way that we can actually find a way to remediate the PRT failure and deficiency? And that's kind of what they're trying to incorporate with the STEEL program. The long term, which we haven't gotten there yet because we haven't identified all the subgroups that have experienced grit and respond differently to failure, hey, is that marginally faster runtime worth that decrease in academic performance? If there is no long benefit, assuming that these results hold true, should we have those higher standards in the fleet than the fleet at the Naval Academy? But yeah, that's all I got, so I'll open up the questions. Yeah, so it's going to go back to the, data set. So I only said PRT run failures. That's pretty much why, because only 3% of people fail to run, and that's what people fail the PRT on. Like, the amount of people who fail push-ups and curl-ups relative to run is far less.
So I know in the past few years, there's been a lot of discussion about changing the PRT standards to reflect the fleet more. Have you factored that into your research, and how do you think that would affect the way you're looking at the research?
Yeah, so since the results changed, so 2020 was the day that they changed it from, this is curl-ups, push-ups, and a 1.5 mile run. We do the plank now. This only goes from 1999 to 2020. So those like factors like have the fact that we changed the PRT standards and the fact that we changed the events, it is absent of this data set.
How would having a randomized PRT affect the data set? Like, instead of having a scheduled one, if someone were to say, okay, I want to take my, or like they get told they're going to take theirs at a certain day, how would that affect it?
The way we incorporate PRT results in this, because we have the brigade PRT, and then prior to 2008, where there was a bunch of people who just took it. It was like on like more scheduled basis, like take it every other week or something. And they're just going to get incorporated into the data set. That's going to be more of a conversation of how people perform, I would say, not necessarily the causal effect at the failure cutoff. This is more of like, hey, what happens if they actually fail?
Did you look at any other sort of results besides academic Cooper? Like, I know military Cooper is a little weird because it's like academic. Did you see anything else besides academic Cooper?
Yeah, we try to do academic Cooper because the PRT is factored into our overall order of merit and then our military order of merit. So it's kind of weird when you fail the PRT, it's going to have a systematic effect on those results. So we focus on academics. That's kind of what we're trying to get at with the NSIPS data set, which is the fleet outcomes. We can then apply the exact same methodology to look at like fit reps, promotion rates, time in service, and all those various outcomes. We did also explore like the covariates and whether or not, like if you're a Marine Corps select, are you more likely to go to Marine Corps? And we're kind of exploring with those. One is a test to see that the two groups are different, the two groups are similar to make sure that's like a proper application of the methodology, but also, hey, like, should we expect more Marines when we should see less people go Marine Corps when they fail the PRT, that kind of thing. Yeah, it's kind of with like the two-stage like the regression discontinuity. So this is like the standard one, and you apply the optimal bandwidth. But then this is like a way to test for it. Like there's assumptions with all these identification strategies. Like for an RDD, you need a continuous cutoff, and that's kind of the issue we run into here. It's not continuous; it drops off. So that raises a red flag, and you can test like those red flags with a variety of different mathematical approaches. The one I use here is the CGM density test, and that kind of shows that there is manipulation, and they reject the p-value, the null hypothesis at the 1% level. So that makes you adopt the RDD, the donut RDD, which you can then do the exact same thing. The same with 2C's we squared. They have 3 assumptions with it. So like those diagnostic tests at the bottom, basically what we're looking for there is we want to reject the null for the Hansen J, which is showing exogeneity, and our instruments are exogenous, and then the weak identification and under identification test show that our instruments are relevant. So we want to see like a KPRKF value of greater than 20, and then same with like the under identification test. We want to see that to be statistically significant. Those are the way you can test it mathematically. Yeah. Yeah. Yeah, it's just the application of the research. We're looking at the causal impact of failure. Like the people who max, they don't fail. So they're not going to ever experience that, that adversity and develop those non-cognitive skills. We're looking at those people who are marginal because they're also more of a better comparison group. If we include the people who max, we're comparing like apples to oranges. But when we're comparing people who barely pass to barely fail, that's apples to apples. They're fundamentally the same. Yeah, that's a question of the stakes, because with PRT failure, like there's some serious stakes to it. If you fail it, you're going to go appear in front of the superintendent, especially if you do it multiple times, you're going to get kicked out. You fail a class, you're unsat, and then you kind of just retake the class. So there's just the effect of failing a class is just far less than the PRT, so it's more of a data set limitation as well. Yeah, so under the current PRT, since it's just a new standard, they're not failing anymore. So they just effectively shifts that donut RDD to the right a little bit. So now we have even less observations of failure, which kind of hurts the empirical estimation. Correct. The runtime matters in terms of getting rid of the people who max greatly and those who fail greatly. Yeah, you're just trying to find people on that cutoff. Like ideally, like imagine duplicating yourself. One runs you both run the PRT except one of you trips right before the finish line. You're fundamentally the same in all observable and unobservable characteristics, with the exception of one receives the treatment, the other does not receive the treatment. So since you're fundamentally the same across all metrics, the only thing that could cause the difference in your academics is the PRT failure. Sorry, I saw your hand go up. Do you have a question still? Right, so that's going to be the subgroups. That's what I'm talking about when we talk about subgroups. It's like, hey, there's people respond to adversity differently. Like if you're a straight A student and you fail the PRT, you might still be a straight A student. But if you're a person who has a 2.5 GPA, failed the PRT, might have a short run decrease in academics, they might have a higher increase in their academics because they're capped at 4.0, but the people who are on the lower end, the keeper spectrum, they have more room to improve. So that effect might be more clear.
Apart from the PRT failures, did you look at the absolute correlation between grades and PRT? You score higher on PRT, you get higher grades, or do you look at that down?
See, you can kind of see it on this one. You see it, the people on the left side, it's kind of more of a downward trend, but the right side of failure is kind of all over the place. You got high performers and you got low performers.
So generally, a higher keeper is going to have a higher
It's correlative. Yeah, I mean, based on what we're looking at here, they tend to be. That's kind of why you take out the maxers, right? Because the maxers are fundamentally different than those on the margin of failure. Because if you look at them, I'm sure it's going to be kind of a similar story. It's like they're going to be all over the place. Yeah, I forget. There was a graphic I had for it, but it kind of shows there's like a lot of heteroscedasticity on the left side and the far right side, showing it just goes all over the place, and then you kind of narrow it in the middle, and then, yeah.
Did you ever look at different time scales rather than just the average of that whole year span? Like if you saw any trends within a couple decades, if PRT was getting easier, harder, requirements, that kind of thing. Did you see any of that?
Well, that's the nice thing about this data set is 1999 to 2020. That's the exact same PRT across the different. Because if that happened, like in the middle of the data set, like say we changed the standards in 2007, we're now confounding our estimate based on the PRT. Is it the fact that people are failing because of the PRT, or is it because of the different test? So it kind of messes with that a little bit. Is it the same?
up, man? Read it to me. Say the question. Yeah, so my name is Ryan McKee. Thank you all for coming. I see a lot of company mates, friends, and some family here too, so I'm really looking forward to showing this project off. Feature engineering for generalizing near maritime atmospheric optical turbulence machine learning models. And, I want to thank my professors, Professor Charles Nelson, Cody Barnell, and then John Burkhardt as well. So there's been a couple other presentations that have been about lasers and about turbulence, and they've had one thing in common, is that he was one of the advisors for those, so I think he likes turbulence. But yeah, so a couple different topics we're going to get to in this talk. I'm going to go ahead and just get started. Directed energy systems in the U.S. Navy. So the U.S. military is facing increased drone threat around the world. We're seeing this in Ukraine and also with our troops in Iran. And there's a lot of threat to our naval vessels and other assets on the ground. And we have U.S. interceptor missiles that work very well. They're very, very competent, but they are just expensive. And so if you look at the economics of that war, multi-million-dollar missiles that work really well against $20,000 to $50,000 drones, eventually we're going to lose that battle, no matter how good those missiles are. So here's some of the missiles that we do use right now. The SM-3, the SM-6, again, both very competent systems, but they're just very pricey. And a ship can only contain a certain amount of those. Eventually, you need to go restock, need to go resupply, and they have to go refit before they can keep fighting that war. So to overcome these limitations of both cost and loadout, the Navy is looking at prototype naval lasers. So here are three different examples. We have the LWSD system on the Portland, the LAW system on the Ponce, and then the Helios laser, or the Preble. I'm sure there's more systems that are out there, especially now at a classified level. I'm sure there's a lot more, but I'm not cool enough to know that yet. So there's a lot of development that the Navy is doing with laser weapons to try to make these things work and have a more cost-effective way for air defense. But there's one catch with these, and that's the atmospheric effects on directed energy. So there's scattering, absorption, and then what I'm focusing on here is atmospheric optical turbulence. And that is quantified by the refractive index structure parameter, the CN squared value. In this middle chart here, you can see this white is laser power. So an ideal situation would have that laser power nicely focused in the middle of that red circle, be a nice white hot dot as it melts through that paper. But we don't see that. Because of turbulence, we see that laser power being spread out greatly and being moving around on that target board. It's not aiming where you want it to aim, and it's not pumping all that power into a nice tight circle. You just get that instead. So this is how turbulence comes about. First, we have this Gaussian wave profile, all the energy in the center, which is where you want it to be. We have a nice smooth wavefront here as it exits the laser aperture. But as it starts to move through the atmosphere, it encounters these turbulent eddies. And these eddies come from the sun heating the ground or heating the water, hot air rising, cold air sinking, causes mixing. That mixing air has slightly different densities and slightly different indices of refraction. And so as the light propagates through those different turbulent eddies, there's small variations in the index of refraction and small redirections of the laser light. Those repeated micro-directions of the light result in spreading and inconsistent power distribution. And that's how you get graphs like this. Here, this is something that I made myself when I was in a laser elective with Professor Nelson. This is just no turbulence, nice laser firing 50 meters indoors. So very, very little turbulence. It's still a nice circle and it stays pretty tight the whole way through. However, as soon as you introduce turbulence, you get some structure like this. Nothing else changed except for the introduction of turbulence. We go from that nice circle to much, much wider, and the power distribution is all out of whack. It's not at all what you want to do. So over here on the right side, we have a typical range of values for CN squared as it increases with altitude. At very high altitudes, turbulence is not that bad, and naturally it's really, really bad where we want to do stuff with it. So in the sub 1 kilometer range down there where the Navy operates is at its absolute worst. This is very, very relevant for the U.S. Navy. So if we're trying to use directed energy weapons to take out drones or take out missiles, every single ship captain should know, will my laser look like this or will my laser look like this? So that is what I'm trying to figure out here with modeling atmospheric optical turbulence with machine learning. We're going to talk about machine learning. First, we need to talk about our data sets. So I have two different data sets here. One's from San Diego. On this right side is a map here. It's right on the coast of the Pacific Ocean. And we have 13 months of data, so it's very, very extensive, very full. It's an awesome data set to work with. Very similar thing in Annapolis. collected by a previous Trident scholar who worked here, and he collected his data set just over the Severn, firing from the sailing center out to one of the radio towers on Grayberry Point. So those are my two data sets that I'm working with here to try to predict turbulence in the area. This shared features list over here, that's all the variables that I have from the instrumentation, all the measurements that I was taking. Air temperature, ground temperature, relative humidity, and wind speed. And then I broke up the wind speed into two different components. So temperature, humidity, wind speed. Very standard measurements that we got just from these simple measurement systems. So these are two models that I trained about a year ago on this data. On this left side, this is over a typical day in San Diego. So this is time on the bottom, going from about 6 a.m. down to 6 p.m. You can see the red is the actual value of turbulence, and the blue is the predicted value of turbulence. It follows it very, very well as it goes this diurnal cycle. So we see a dip here for sunrise, crests at noon, and then has a dip there at sunset. This is beautiful. It's really as good a day as you can get. This is from San Diego. On the right side, this is a completely different way to visualize these results. Instead of looking at one day, it's looking at the entire data set, all 13 months together. On the bottom, we have the actual value. That's what the real value of turbulence is. And on the y-axis, we have the predicted value, what the model said it was. So this red line here in the middle, that's where you want to be. You want to be as close to that as possible, because that means you're predicting perfectly. And as you can see, it works pretty well. It's pretty tight to that curve initially. But so over here, this is two bits of analysis that I did on this, and I want to draw out two important things from this. First, these green charts here, those are feature importance. So that's how important each of these variables were to the model. And so if you look at both Annapolis and the San Diego data sets, the difference in temperature between the air and the ground were the most important in both regions. But if you look at rank 2 through the bottom on both of these charts, completely different. The order is different, and there's really no carryover between both of these regions. And also, if we look at these red and blue charts, these are correlation matrices. You don't see similar patterns at all between these two regions. So these two bits of analysis are just telling us straight away that Annapolis and San Diego are not similar climates at all, which makes sense. If you guys have been to San Diego, you know it's just perfect weather. You walk outside and it's awesome. But Annapolis is wet and it changes. Every single day is different. So Annapolis and San Diego, we know they're fundamentally different. That's what this analysis is saying. And that's what these models are saying too. When you take this Annapolis model and you test it on the Annapolis data set, it works very well. However, as soon as you take that Annapolis model and you test it on the San Diego data set, it has no idea what to do. You get really, really good predictions here, but as soon as we move that model to somewhere else, it has no idea what to do, because these regions are fundamentally different. There's different physics, there's different relationships, different patterns that are causing these issues. So what works for one location's model does not work for another. And this is not going to work for the U.S. Navy. The Navy doesn't care if we have a model that works really well in San Diego. They're going to need one that works in the South China Sea, or works off the coast of Somalia, or coast of Iran, or Israel, wherever. They need models that work in other areas and not just here. So what now? We know that they work where they're trained, but they don't work when you test them in a different spot. We also know that each region has different physical relationships and different meteorological patterns that govern the region. So the question I ask myself, is there a feature or a set of features that I can either find or create that remain consistent between these two regions and can make this work, can smooth out the predictions over both of these regions? So that brings me to the heart of the issue here, generalizing these machine learning predictions. So I tried two different things here. First one did not work at all. The second one actually did work. So I'm going to talk about the first one first, because I learned some good lessons from there. First thing I wanted to do was do the bulk approach. I wasn't sure what feature was going to be important or what combination of features, and I didn't know what it was going to do, so I tried to find out every single possible feature that could work. And so I used a couple different algorithms here to go through and create all of these, systematically go through and make every single one and see how they worked. So this is an example of something I was looking at, air temperature divided by wind speed plus relative humidity. Doesn't make sense. It's a total guess. but what I was doing was a whole guess and check model systematically, because maybe it did work and it doesn't make physical sense. That was the inspiration, and I used a couple different functions here in Python to accomplish that. Formula features, GPLearn, which is a genetic programming library, feature tools, and then I made my own custom function. It was all very heavy computation to try to find every single possible feature, and it didn't work at all. So I was met at every turn with performance bottlenecks and just memory leaks, and it was all terrible. And the features that it did make were very repetitive. It was just copies of itself, and it wasn't actually anything meaningful. Whenever I actually used these to test a model, to train a model, it was worse than when it started off. There was no added benefit to the model, and this was just a bad way to go. Part of the thing that's concerning here is that these two equations, these are two of the most individually high-performing features that were made by the model. If you look at these, none of these make sense. And there's a bunch of, if you look closely, there's some mathematical stuff that doesn't make any sense at all. Like we have triple absolute value bars here. That's meaningless. Doesn't mean anything. And also it adds stuff and then subtracts it away right away. The model has no idea what it's doing. It's guessing. There's no intuition behind this. It's just trying to squeeze every last drop of performance out of these features. And so what we're getting here is finding that super feature. I found the hard way was just unrealistic. This was not a good way to go. Two hypotheses for why this didn't work is first, the nonlinearity of the tree-based models that I'm using for this project. These decision tree and random forest models, they make their own pseudo-mathematical splits to try to divide up the data. As soon as you feed it its own mathematical equation, it has no idea what to do and it just confuses the model and makes it too complex. Also, regional specificity. I was taking the specific features for the specific data set, taking the specific equations from it, putting them together, and then expecting to have something that would work for everywhere. No, instead I got extreme regional specificity, and it barely worked in the spot that it was trained in. This was a terrible way to go, but I learned two very important lessons from this. First, if I was going to use an equation, it needed to be simple. It needed to be understandable. And I couldn't make it too big or complex or else it would just confuse the model. So it needed to be a simple equation. Second, I learned that I don't want these features to be too specific into one region. I needed to go the other way. I needed to go generic, get very generalizable. And so where that took me is back to physics. I borrowed some equations from there, these equations down here in the bottom. All of these are simple, and they are either dimensionless ratios or gradients. These are generic. They're not specific to one particular region. And instead of a model looking at temperature above or below 90 degrees at a threshold, it's looking at the difference in air temperature and ground temperature. That doesn't change between Annapolis or San Diego. You can still have a 5-degree difference in either spot. So instead of being specific to one region, it's working everywhere. So I took these original features lists, the temperature, the humidity, the wind speed, and I used these equations to turn them into physics-informed features. The air-ground temperature difference, the vapor pressure gradient, which is just the absolute value of moisture in the air, the wind stress, which is a proxy for wind speed, the marine wind ratio, the Bowen proxy, which is a ratio of the sensible heat flux to the latent heat flux in an area, and then the temporal hour weight, which is just a mathematical way to represent the time of day. So I turned from these to these, just using these physics equations, and it worked really well. So I want to highlight two things for you real quick. This is the Annapolis model training on the Annapolis testing on the Annapolis data set. From your chairs, these probably look very similar. These are the original features, the simple ones, wind speed, humidity, temperature, and these are the ones the new features that I created with physics equations. But over here, you can see the difference in error reduces it by 60%, so very substantial. And in San Diego, we see a very similar thing. Again, visually, it probably looks similar from your chairs, but we see a 58.9% decrease in model error. But this is just where the model was trained. We already know the models work well here. The real kicker is what happens when you test them on the other spot. So I'll highlight these again. This is the Annapolis model training on the San Diego data set. So it's testing on the place where it wasn't trained. Here we have terrible error. The model has no idea what it's doing. But down here, again, probably hard to see from your chairs, but it's actually following the trend line of the perfect prediction. We go from an error of 1.83, which is enormous, down to 0.6, a 65% reduction. This model is usable. This actually gives you valuable information compared to this one. San Diego, similar thing. This is the graph we saw earlier, which is terrible. You might as well just pick a random point. It'll be better than the prediction. But down here, you can see it's actually following that prediction line now. The introduction of these physics-informed features worked to generalize these models. It made them actually usable. So these are the error histograms for the predictions. On the top left and bottom right, these are the Annapolis model testing on the Annapolis data set, and then also for San Diego. It's much tighter, which is what we expect. It's saying that pretty darn near all the predictions are within plus or minus 0.5 of the actual value, which is very good. So even with the improvements to the model, these are the new features, even with the improvements, it's still really bad when tested in the opposite region. And there's a lot of skewness there too. The San Diego model is under-predicting, and the Annapolis model is over-predicting. Even when you try to correct by introducing these physics-informed features, these are still very, very different regions that need to be overcome by more math, more analysis. So those are the results, but now this is peeking under the hood, seeing what is actually going on here. So first, I want to look at the feature importances. Let's look at San Diego over here first. We still expect to see the air-ground temperature difference as the most important, and it is by a long shot. It's 6 times more important than the next most important. But that second most important is the temporal hour weight, which is the time of day. So in San Diego, the difference in air temperature, or difference in temperature between the air and the ground and the time of day, those are the 2 most important features. And that makes sense. You wake up in San Diego, every day is pretty much the same. There's very low humidity, very low anything else. You wake up and the temperature is very dependent on what time of day it is. Cold at night, hot during the day. So that makes physical sense. The turbulence is dominated by the sensible heat, the heat that you can measure with a temperature, or with the heat that you can measure with a thermometer. So that makes physical sense for San Diego. But in Annapolis, it's a much more dynamic, wet climate. We actually have humidity here. We're on the water and we feel like it. So we see that represented here in the feature importances. The air-ground temperature difference is still the most important, but only half as important as it is in San Diego. The rest of that value is coming from this delta E, which is the amount of moisture that's in the air, or vapor pressure, and then also the ground temp, which for the Annapolis sake is actually water temperature. So air-ground temperature difference, the amount of moisture in the air, and the water temperature. The Annapolis region cares a lot more about water and about the moisture in the air than San Diego does. San Diego has no moisture in the air, so that makes sense. So this is a great sanity check. This is exactly what we expected to see, and this is showing that the models really are different and it's treating them differently. It's treating these regions differently. So this is the next bit of analysis called residual error analysis. Typically, when you look at machine learning, people show you how well their model performed in some case. This is the exact opposite. This shows you how your model messed up, looking at each feature. So I want to highlight a couple of these for you. This is the variable, the marine ratio. On the x-axis, we have the range of values for the feature. So it goes from -1 to 1, and then on the y-axis, that shows the how far away it was from making a good prediction. So that 0 line, that red dotted line, that's where you want to be. The further away you are from that means that it was a worse and worse prediction. And across the line here, it's pretty stable. You can see that the error is mostly localized around that 0 line, and then it's flat all the way through. This is what you want it to look like, and that's not what they all look like. This feature, this is the air-ground temperature difference from Annapolis, and this is a good example of heteroscedasticity, which just means that it has a diamond shape in it. So if you look at the high magnitude on both the far right side and the far left side, it has good prediction. All the predictions are very close to that 0 line. But if you look in the center, the error gets a lot worse, which actually makes sense, because when we have very low difference in the air-ground temperature difference, both of those models, they cared the most about the air-ground temperature difference. When that's 0, when it doesn't exist, the model doesn't know what to do with itself, so it makes a bad prediction. So that also makes physical sense, but it's a good example of what that bad shape looks like, the heteroscedasticity. And this is the final example here of the wind stress. Think of it like the wind speed. When the model has a very, very low wind speed, the error is very bad. But as soon as the wind speed picks up, then the model picks up, knows what it's doing again, and makes good predictions. This is not at all how it's supposed to be. Ideally, you'd have everything be flat, which means that there's deficiencies in the model. So while there's still been improvements over the original, there's a lot more work to be done on honing in these features and bringing them to be the best that they could possibly be. So again, all of this is just on the region it was trained. Now, this is when you test it on an opposite spot. Annapolis on San Diego, or San Diego on Annapolis. I want to highlight a couple here. This air-ground temperature difference that used to be pretty flat is now not flat at all. It over-predicts on both the left and the right sides, under-predicts in the middle. This marine ratio still looks similar, just has a lot more air on it. And then this vapor pressure over here, it has just a nice blob, which is good. It means there's no prediction bias, except for the fact that it's under-predicting pretty severely across the entire way. These features, ideally, would all look flat the whole way across. So there is a lot more to be done with these, and there's room for improvement on each feature. Whether that's adding in another feature that's capturing something the model's missing, or it's normalizing the data a different way, all these things that could be done to improve this residual error. So this brings us to my last few slides here. This is the summary of results. On the native region, when you test it on the place it was trained, we have 60% reduction in error. And on the foreign area, where you test on the opposite area, a 65 and a 42% reduction in error. That means that these models are usable. This is actually much, much better than it was before. It's not just random anymore. However, even despite those improvements, there's still more to be done. This residual error analysis shows that there's still model deficiencies, whether it's a missing feature or whether it's some kind of a cloudy data. What needs to happen is these features and this whole process gets tested on the third place. We say, all right, how does it perform there? Are there deficiencies that we can correct? And we start testing more and more spots with more and more data sets, and eventually we'll hone in on some type of model that really can generalize to every area. So, physics-informed features make these generalized models possible. As far as I can tell, no one's ever done this before. There's no papers posted about it, and this is the first time it's been done. And so, including these physics-informed features instead of the original, it increases the model accuracy in the place that it was trained and then tested. Also, it increases accuracy in the place where it's tested opposite, which is the model generalizability. If we have a generalized model, that means that every ship captain can know what the turbulence looks like around the vessel. They can know if their laser is going to be a small circle or it's going to be really wide and unusable. That increases the ship captain's situational awareness, so he can know, should I use the cheap laser, or do I need to rely on one of my very limited, very expensive, but highly capable air defense missiles? It lets him pick confidently, do I have time to use a laser, or should I use a missile instead? And this, in the end, saves us money, because we don't need to waste missiles on threats that are not worth using a missile on. And anything that saves us money makes our military better and stronger, because we get to use money in other places. We fight smarter, we fight harder, we fight better. And so all this project is to know, for the captain, is it a good day to fire the laser? That's my project. Thank you. Good, sir. There's more bits of measurement that I would include, for sure. I would include much better measurements of the ground temperature, have some sort of radiometer. That's just like for COVID we use like the point and shoot thermometer, something like that, just points to the ground. That would be much better because you get the actual ground temperature instead of the temperature close to the ground. That'd be nice, and then also having some kind of solar panel that measures the solar radiance at the area, how much sunlight's hitting the ground there. That'd also just be helpful because I'd see if that changes anything. Those are two things I'd add: radiometers and then solar radiance. That's what I do. Thank you. You have one? Sure. Thanks. Yeah, so you're saying have like multiple models for different regions of the world? Is that what you're saying?
Wherever you are, say,
Yeah.
you choose, like, is that, even if, is it easy to find, to identify the features? Is that just simple measurements, or?
It's fairly easy. I mean, I showed you on the feature importances. You can see it was wildly different for both Annapolis and San Diego. So in theory, if you collected a data set for a region, and then looked at the feature importances, you could see that. The hard part is that was a 13 months and 15 months data collection. Really hard to do that in a war zone, especially if you don't know where the next war is going to be. So that's part of the importance of just trying to generalize to every region, because you don't know where you're going to be next. Sure. Sure. Yeah, it might be. That's going to take more analysis into what these different regions look like and how exactly they are different. Because, I mean, I could guess on what are two similar regions, but for all I know, off the coast of Israel and off the coast of Iran could be wildly different, even though they might be similar. I don't know. So it could be a pursuit, but it's something that should be figured out in the next probably decade or so. It's a good question. I don't know the answer to it yet. Somewhat consistent, yeah. It was. Yeah. Both of these data sets shot upward about 150 meters over the course of their propagation. So roughly, in the grand scheme of things, roughly flat, but not exactly flat. Can't do the trig in my head, but it's about 2 kilometers and then 200-meter gain. So roughly. About. Yeah, so it actually only makes it better. If that plot I showed earlier that had the altitude with the CN squared, turbulence only decreases as you increase in altitude. So if anything, the model would tell you it's much worse than it actually is, which means that you shouldn't, unless there's some edge case, you shouldn't need to worry about using the laser when it's not allowed. Yes, you're more likely to use a missile when you don't need to than get shot in the face. So, yes, ma'am. Yes. Oh, gosh. Thanks, roommate. So what we see here, his question was asking about the shapes of both the air-ground temperature difference here in the Annapolis data and also the San Diego data. Neither of these look ideal. Both of them should be flat in an ideal world, but they're not. Both of them have similar shapes. The thing that we do see that's consistent between both these regions is the neutral stability region, which is when the air-ground temperature difference is 0 or very close to 0. That's when the model can't rely on air-ground temperature difference to make a prediction, because it's 0 or just is non-existent in that case. So what does the model do in that case? It doesn't really know in those rare circumstances. And so what we have here is in both the San Diego and Annapolis regions, both the model error is bad in both of those. So yeah, it definitely speaks to similarities between both regions in the neutral stability zone. Thank you for your question, Karsten. All right, anything else? Sweet, thank you very much.
Rory, I can't stay the whole time.
Oh, that's fine. Oh, excuse me, Professor.
Rory is continuing a project that was started with his external collaborator in 2015, so we've been working on it for a while. Rory's hardworking and soft-spoken, and you know, between his co-advisor and I, he has a hard time getting it worded edgewise, but he has held his own, mastered complex physiological mathematical material, and done a really great job on this. And hopefully we'll tell you at the end, he's had this paper based on his work accepted at a major IEEE conference, so we're very proud of him.
All right. Thank you, Professor, for that introduction. Once again, I'm Midshipman First Class Rory Smith from the Robotics and Control Department. And my Trident project over these past few semesters has been using machine learning to identify the sensitive parameters of a type 2 diabetes dynamic model. And I'll explain exactly what that means here in the next few slides. So I want to thank my advisor on this project, Professor O'Brien and Professor Jaramillo, as well as our external collaborator, Dr. Eileen Tatum, who was previous Trident using this model. So many of us are probably familiar with what diabetes is, but I'll quickly define it as a chronic disease that results in high blood glucose concentration. And that's an issue because having a high blood glucose level can erode the blood vessels and lead to cardiac disease, kidney failure, and amputation, among a host of other negative conditions. So there's pretty clear reason and motivation for why we should address it. It has disproportionately affected the veteran community and affects millions of Americans. So many of us have heard of the two big types of diabetes. You have type 1, which usually appears much earlier in life and affects a smaller percent of the population. And in this case, for these patients, they're unable to produce insulin. Insulin is that hormone that facilitates the transport of glucose in the bloodstream into your muscle and fatty tissue cells. And you need glucose to move into those cells for cellular respiration, which is the moving, breathing, thinking, working, everything you need to do to live. So for these patients, they're unable to move that glucose out of the blood and into those cells. Conversely, for type 2, which affects a much larger percent of the population and appears later in life, it's not that these patients can't produce the insulin themselves, it's that their cells are insensitive to the effects of insulin. So they're having trouble moving those glucose molecules into the cells, and their cells are not receptive to it. Now, the interesting part about this is the treatment methods. So for type 1 patients, their main treatment method is just external insulin. So you've probably all seen someone get an injection of insulin that is supposed to replace the insulin they do not create. However, for type 2 patients, there is no set solution. Some of them do take insulin, but that is liable to cause hypoglycemia, which is a serious case in the short term. However, you have heard of big medications like Ozempic and Zepbound, which are currently in the news, that are new treatment strategies for how we can address type 2 diabetes, but there still is no consensus on what is best. So this diagram depicts the glucose-insulin environment pretty well. You can see there's an oral glucose intake, or a meal like we call it, and it moves its way through the gastrointestinal tract and eventually into the plasma or the blood. Now, what insulin does, it is supposed to facilitate the movement of that glucose from the bloodstream and into the muscle and adipose tissue cells. Adipose meaning fatty tissue cells. And so, like I talked about for type 1 patients, they are unable to secrete insulin. So this part of the body is disrupted. So they can't facilitate that transport, but luckily we can give them external insulin that does the same job. However, for type 2 patients, it's not that they don't secrete it, it's that they can't receive it by these cells. These cells are insensitive to the effects of that facilitating insulin hormone. So what do we do about this? There's a pretty clear problem here, and how do we address it? Now, this model gives us a fascinating chance to look at the glucose-insulin environment in a mechanical way. You can see it as if it was a sink. There's glucose coming in through the faucet, at that oral glucose intake, and then glucose coming out through its utilization in those cells. And in the perfect world, you want to minimize how much glucose or water is left in that sink. You want to make sure it's flowing straight through. And so that's what we set out to do in this project. And we needed to do this without having to go out and get a real patient data set, because there are plenty of obstacles with controlling experiments and getting the approval to use real patient data. So in order to do that, we had to use a dynamic model that allowed us to simulate our own virtual patients. So we could create computer simulations that were realistic and provided realistic data for these diabetic people. So this brought us to the dynamic model. What is a dynamic model? So the best way to explain it is that equation of motion, or some way that we can model this movement of glucose and insulin through simple mathematical equations. And you could think of this just in the sink example. There is some way mathematically with the glucose coming in and the glucose going out that we can describe that concentration of glucose left in the sink in a mathematical expression. Using those expressions, we can simulate some real patient data for these virtual patients in a way that is accurate and physiologically capable of being analyzed. So once we have all this virtual patient data, we come to the point where we need to draw connections, because what we want to do is find, okay, which process within the body is most important and most impactful when determining someone's diabetic health. Because if you're going to create a medication to help cure diabetes, what you would want to do is address it at the part of the body, the process that is most important, that is most impactful on someone's blood glucose concentration. And so what we have to do is we have to draw connections between the data we just generated and collected through this virtual patient simulation, and then those processes, those parameters of the equations of motion that are X variables. So when we talk about statistical models, think of them as trend lines. So in this case, we're trying to draw a connection between our X variables, our processes and parameters within the model, and then our data that we collect is the Y variable, so that glucose concentration. And we want to see how does each process impact someone's overall diabetic health. This brought us to the Dalleman-Cobelli meal simulation model of the glucose-insulin environment. So this is an FDA-approved dynamic model that is a substitute for animal and human testing. So everything we produce with this model is viable. It's realistic. So we can test this and we can publish the results as evidence of what could be possible. And so this allows us to simulate thousands and thousands of conditions across several different meal inputs. So we can give a virtual patient a meal and watch how they respond. Like I talked about, these dynamic models are simply just equations of motion, but they're much more complicated than a single equation. 27 interconnected differential and nonlinear equations make up the DMC model, which are a lot, and you don't want to solve those by hand. So not only are there equations, but there are parameters, these processes within the body that affect someone's glucose and insulin levels. And so what we want to do is find, okay, which one of those parameters, which one of those variables is the most important? And you can see those variables or parameters represented in the equation right here. So for example, K1 and K2 are rate parameters that govern how glucose moves in and out of the plasma and tissue, those cells. And you can see those graphically depicted right here in this representation. So it's not like we're just coming up with equations that fit the data we had originally. No, we're coming up with real physiologically significant parameters. Those K1 and K2 values represent real quantities that you could change. And that's what we set out to do. So this is the overall project flow for what I've been doing for the past few semesters. And while there are many other parts to it, many other experiments and trials we've run, this is what I thought was the most significant. So like I talked about, the first thing we had to do was generate these virtual patients. We wanted to create a population of virtual diabetic people who could represent a variety of situations. So not everyone was going to look the same. We wanted people right on the cusp of being diabetic and people on the extreme end. And from this, we wanted to then see, okay, if we can recreate the DMC model, those equations of motion I just talked about, can we give each of these virtual patients a single meal, a simple single meal, and watch how they respond? And From this, we should see that each of these patients who is unique should respond differently because each of them has a different parameter value or different parameter values that were set according to that distribution and variety of population I just described. So from this, we can collect data on them, we can observe how they respond, and we can draw connections between those parameter values they have and how they performed in response to those meals. And this allows us to connect to current and future medications. So what are people doing right now, and how are they addressing different processes within the body? So the first step, like I talked about, was that patient population generation. So fortunately, the DMC model paper gave us real-life parameter averages for each of those 35 physiologically significant parameters. So when they created those equations of motion, they were going off of real data from real people. And so they collected some average parameter values for each of these people, for both the diabetic and non-diabetic cases. And so using this, we were able to create normal distributions for the diabetic population. So then you can see that in figure 7, where this is the distribution volume of glucose for a diabetic population. You can see that it's not the same for every patient, and that's important. We want to create a diverse population of diabetic people. From this, we were then able to create and start building the DMC model because we wanted a way to actually run these patients through an experiment. And we were able to do this through MATLAB Simulink, which is a way to graphically and physically put together blocks that describe those differential equations, those equations of motions of the DMC model that I described earlier. And in this way, we can run time response experiments to see how these people respond to an input meal. But first, before we could do that, before we could start testing this huge, large population of people, we had to actually validate what we had created. We had to make sure we built the DMC model in Simulink properly. Because if you go back, each one of these blocks is made up of a constituent number of interconnected graphs and blocks itself. So it's extremely complex, and we had to make sure we connected them all right. So the big part of this was finding out, okay, how do we do? And the thing is, this graph right here in figure 9 is real data, real patient data from the DMC model paper. And you can see the type 2 diabetic curve, the dashed one, is the real data that they used as the evidence for those equations of motion they created. They made those equations based off this data. So we set out, okay, if that's the real patient data from the paper we're using and the model we're using, we should probably try to mirror that, recreate it. And so that's exactly what we did here. You can see our model is this dashed blue line. This is what we did when we gave an average diabetic patient a sample meal the same as they did in this trial. And the published mean is the one from the DMC paper right there. And you can see, okay, there's kind of some variation there. So you would think, okay, there's natural hesitancy. Should we accept this? Is this good enough? And what we kind of realized is that, yes, it is. Because if you look at it, it has the same trend, it has the same steady state value as this published curve right here, and that's what we're going for. We're not going for the ability to predict someone's glucose levels. We're looking for the process within the body that is most important, and that's simply just a function of which parameters are important. And this was further validated by the fact that another group, the Symbiology group, tried to reproduce exactly what we did as well in the green line, and you can see that they have their own variation as well. So we took this as pretty good evidence that we should continue. Moving on, this is where we got to the big part of the experiment, where we gave each of these patients a single lunch, 70 grams of glucose. Think of that as just a simple plate of spaghetti. So this was a fascinating experiment, but also very simple at the same time. Just a single meal, and we could run this for thousands and thousands of patients. As you can see, we had almost 12,000 diabetic patients and 5,000 non-diabetic patients. And we didn't really study the non-diabetic patients, but it was important to create them and run them through the experiment so we could tell the difference between who is diabetic and who is not diabetic, make a distinction within our model. And this allowed us to really collect the data that we need to analyze. This is creating our own data set. But this was also at the same time the most time-consuming part of the project. And as you can see, it took over 2 minutes simply to simulate a single patient. And when you're simulating thousands of patients across a variety of conditions, that gets very time-consuming. But we collected all that data. We found their glucose and insulin values over time. We mapped those curves exactly as you saw. And so what was the next step? We had to finally draw those connections between the processes, those parameters I mentioned, and the output variables of glucose and insulin. Why did their glucose and insulin values change in response to a change in those parameter values? And this brought us to statistical models and a statistical model pipeline that is very standardized and very simple. We started off with a basic linear model, which created general linear connections between each of those parameters or processes and the output. Next, we move on to more of a qualitative approach, the Morris method. This allowed us to finally look at which parameters were generally important when it comes to finding out which of these processes is the biggest, the most impactful. But that is not the best way to find out and rank your parameters, because at the end of the day, we want to be able to put the parameters on a list and say, this parameter is certainly more important and impactful than the next one. And that's where the extreme gradient boosting models came in the XGBoost. And so throughout this process, we use 70-30 train test split and tenfold cross-validation, which are just standardized practices in statistics. First was a linear model. As I talked about, these are basic linear connections where each dependent variable, in this case steady-state glucose, is just a summation of linear terms, where x1, for example, is a simple, just one of those parameter values, and its beta value is that parameter's relative importance. It's a linear importance. And so we collected data on 4 specific quantities: the max of steady-state glucose and insulin values. After speaking with Dr. Tatum, our clinician, she educated us that we should really focus on the glucose concentrations here. Not only steady state, which is used as the baseline and the indicator of whether someone is diabetic or not, but also the maximum peak glucose after you consume a meal, because that has serious implications on someone's kidney health. So we collected data on these 4 quantities and we created models for all of them. As you can see here in figure 14, the steady-state glucose model coefficients, these beta values, are mapped for all the parameters, or at least the top 10. And as you can see, M6, a parameter associated with the basal insulin secretion, has the highest and most significant beta coefficient, but it's also negative. If you take that to the equation, you can assume that if you have a negative beta coefficient for M6 and you increase M6, you're going to sufficiently decrease your steady-state glucose concentration. And this makes sense. If you increase your insulin concentration, you're likely going to decrease your glucose concentration. But these are only linear connections, so we had to find something more complicated. This brought us to the Morris method, where we made that qualitative approach and made those connections not just between which parameters were linear, but which parameters were interconnected, which were related. And that got us a much better idea about which of these parameters were even going to have a single place within the top of our rankings. And you can see that here in figure 15 for the output of one of our models. And so this blue box only selects the top 9 parameters. It shows which parameters generally are the top 9 most important, because the other ones are likely not going to be significant enough to create a medication to target them, because you're not going to want to target one of these bottom parameters with some new treatment method. But that wasn't enough. You can't base a ranking simply off a qualitative method. That was meant to screen out the parameters that didn't matter. Next, we had to move on to the XGBoost. This decision tree model is highly complex and is able to handle the inherent nonlinearities of the DMC model. And from this, we could finally get that ranking of parameters that we wanted, that 1, 2, 3, 4, and so on, where we could point to the number 1 parameter and say, this is the place within the body, this is the process where you want to aim your medication. And that got us some interesting results. So we trained these models for both steady state and maximum peak glucose. And what we found was that at the end of the day, we weren't very great at predicting steady state glucose. And so you could see that kind of by the R-squared value here. The maximum R-squared value we could achieve for steady state glucose was 0.58. And for R-squared, that's something you want to get closer to 1, which means we're not very good with predicting it. So you could say, okay, was this a failure? But at the same time, we had to remind ourselves that this was not the deliverable we wanted. The DMC model was created specifically to predict glucose concentration when given a list of predictors or parameters. That was not our job. The DMC model already exists to do that. Our job was to find out, okay, which process or parameter within the model is most important. We wanted that ranking. That was the deliverable we sought for. Which brings us right here. These is the real results of this whole analysis. As you can see, for maximum glucose, we had KABs, or the intestinal absorption of glucose, was by far the most important parameter. You could see it's an order of magnitude greater than the second most important parameter for maximum peak glucose. So you could assume if you want to create a medication that addresses your peak glucose levels, you should create one that targets KABs. Similarly, we see M6 at the top of the steady state rankings again. So maybe we can conclude that M6 is our parameter. We want to target M6. So this brings us to kind of make connection between what do these parameters actually mean, because I've just been throwing variable names at you. You can see in this table, table 4 right here, each of these parameters are color-coded according to the value that they change and correspond with. And you can see that for steady-state glucose, for example, insulin kinetics, insulin secretion, and endogenous production are the processes within the body that have the biggest effect on your steady-state or basal glucose concentration. Basal meaning your fasting level, and that's what you measure when determining and making those tests if you're diabetic or not. So you'd say, this is really interesting. What are we going to do with this information? If I was going to create a medication, it should probably aim at these 3 processes, right? Well, it's interesting enough, we already do that. So we talk about current medications in the news like GLP-1 and GIP, so Ozempic and Zepbound, which are all over the place and do exactly what I just mentioned. They increase basal insulin secretion, they lower endogenous production of glucose, which is the production of glucose from the liver when you're fasting, and they also decrease the rate of appearance from the stomach. So you're decreasing the amount of glucose moving into the bloodstream and making you feel fuller sooner. So this was an interesting moment in the project because what we found was extremely interesting, but also just simply validating the research that these doctors and clinicians already knew. Did we find anything new? That's what we had to find out. And so that got us thinking. If we could verify and validate these, billion-dollar medications, what implications does this have? Could we do this for new medications? So triple agonists like retatrutide are targeting glucagon receptors, which are still undergoing, last phase trials and could be used, and we could use the DMC model to simulate these things. And that's something that we haven't heard a lot about because we proved that we could simulate those GLP-1 and GIP technologies using the DMC model. As I talked about, if you want to change your steady-state glucose concentration, simply increase that M6 variable. And you can do the exact same thing for those triple agonists. So there's a lot to go with here. Where can we bring this? So we're going to bring it to Toronto in July, where we're going to talk about these preliminary results and our basic connections between those diabetic medications, those big name stuff, and the big parameters we identified. We have that ranking. That is our deliverable. We can sit there and present these results to doctors and clinicians and recommend that if you want to simulate your new drug, your new treatment, you could probably do it with a DMC model. And we're here to do exactly that. And so over the summer, I'm going to continue to be working on this project and analyzing what we can do next. So in conclusion, you saw how this project took a vast range of thousands and thousands of diabetic patients and ran them through a single meal trial. Well, this was a basic trial. It showed how each of these patients could respond to the input of glucose into their body. And since each patient was different, had a mix of parameters and capabilities within their body, this showed we could quantify how each of those processes within the body directly had an impact on glucose and insulin values. And that's what we came up with that ranking. That is the deliverable we have and what we're going to present to researchers and doctors. So thank you everyone for coming. Are there any questions? Yes. Thank you, sir. No, thank you. That's a good question. So fortunately, the DMC model paper provided us those averages for both the diabetic patient and also the non-diabetic. So let's see if I can get back there. So I specifically put this plot up here because I needed to create 2 distinct populations. So I created both the non-diabetic and diabetic at the same time so I could make sure one group was diabetic and one group was non-diabetic. And this was extremely beneficial when determining our results and determining which ones were viable. Yeah, that's a fair question to answer. The main group we wanted to analyze here was, of course, type 2 diabetics because that's the issue we want to address. But it was as I talked about, computationally taxing to run all these people through the model. And the healthy patients or the non-diabetic patients were not a group we were really interested in because we could simulate their data to a certain extent, but we wouldn't be able to draw many conclusions from it. And it's important to note that the DMC model was specifically created for type 2 diabetic patients. So yeah, the non-diabetic patients didn't run exactly too well through the DMC model. Mom? No, that was interesting to note that renal function did not come up in the top few variables, which is something that is currently being studied. A lot of people see a huge connection between diabetes and kidney failure. And so, like I talked about for maximum glucose, it is important quantity to track because you want to minimize how much glucose has to be excreted through the kidney. It didn't show up in our analysis, but it is certainly a quantity you have to track. Yes. Thank you. Oh, maybe that's a career for the future, I guess. But yeah, that's a good place to go. And of course, we're going to Toronto this summer, so we'll see what rolls from there. And I'm happy to keep working on the project. Thank you. Yes, sir. Yeah, I think that's an interesting thing to consider. And it was kind of troubling for us because a lot of that information is proprietary, so we can't see behind the curtain. And I'm sure, hopefully, they are also simulating their model in this way or have some even more complex model that they can run. But that's nothing I can see. And I think it's just really fascinating that we could get to the same place with a much smaller budget.
service assignment is Navy pilot. She's attending flight school in July. She's presented her work at two AAS, American Astrological Society meetings. It's the first one, including a press conference that she gave on the discovery of a newborn quasar jet.
Hi everyone, thank you all for coming. Today I will be presenting on analyzing host galaxies of quasars with young radio jets to determine jet triggering conditions and the impact on galaxy evolution. Over the course of this talk, it's going to be really technical, but I want to just bring everyone back to these two key questions of how do galaxies evolve, and also just where do we come from in this galactic evolution. Let's get started. Galaxies are these massive collections of gravitationally bound stars, shown in this white light here in this image of Hercules A. At the center of galaxies are supermassive black holes that are millions to billions of times the mass of our sun. When these supermassive black holes intake and feed upon the interstellar dust and gas from their host galaxies, they are deemed active galactic nuclei. Active galactic nuclei can also exhibit radio jets in the pink emission features you see here. However, we don't quite understand how that feeding mechanism occurs. The most powerful of which of AGN are quasars, and they have extreme luminosities that outshine their host galaxies. We don't quite understand, though, how that feedback mechanism affects its host galaxy as well. So we set out to determine the jet triggering conditions of quasars and their impact on how they affect their host galaxies. Here's an overview of what I'll be covering today. We'll begin with covering the necessary background to understand my project. Then we'll cover the data and observations of my sample of quasars with newborn radio jets we found. Then we'll cover the experimental method broken up into three key phases, and we'll get into the results and discussion and the implications of our findings. So let's go back to that image of Hercules A and zoom in on its central supermassive black hole. So we see the supermassive black hole is accreting matter via an accretion disk here, this dusty disk here. In this accretion disk, it can heat up the dust and matter to extreme temperatures and create a plasma that emits that extreme luminosity of an active galactic nucleus. And at the magnetic poles of this active galactic nucleus are radio jets. These radio jets emit via synchrotron emission, which are electrons orbiting about magnetic field lines that give off that emission. Like I said previously, we don't quite understand the fueling mechanism by which this dust reaches the central supermassive black hole to trigger these radio jets, and that's what we set out to find. Furthermore, only 1 to 10% of the quasars in the known universe exhibit radio jets. So this begs the question, why do only some of these have jets, and how are quasar jets triggered? There are two main forms of this argument amongst the astronomy community, the first of which are external interactions between galaxies. Normally, galaxies are extremely far apart, but over billions of years, they do have the possibility to come close enough to interact with one another or even merge. The simulation you see here on the left depicts two galaxies coming together and merging to become one. During this process, they can disturb their internal host galaxies and cause that interstellar dust and matter to infall to that supermassive black hole and trigger those newborn radio jets. Another form of this involves tidal interactions between a companion galaxy and a larger massive galaxy. This companion galaxy orbits about the larger massive galaxy and causes gravitational disturbances within the larger one that causes interstellar dust and matter to infall to that supermassive black hole and trigger those radio jets. Both of these processes cause extremely disturbed features in the host galaxy, as shown in this image here of a extremely long and asymmetric shape in this galaxy. This is called a tidal tail. It is a tail of stars that have been pulled out from an external interaction with this system. Alternative to external interactions are internal processes within the galaxy itself,
also known as secular processes. This image on the left here depicts a radio-loud galaxy, meaning it is emitting radio jets. And zoomed in here is the image of in-spiraling interstellar dust and gas towards the center, shown in those red and yellow features there. Another way this happens is through bar-driven fueling in this image of a spiral galaxy shown here. The spiral bar guides interstellar dust and material towards that supermassive black hole to trigger those newborn jets. A metaphor I like to use for this is think about your kitchen sink and you have water running and that water is funneling towards the center and you drop a stick in there that guides any food particles towards that drain. Whether radio jets are triggered by external interactions or internal processes to the galaxy itself leads to this even bigger question of how these relativistic jets affect their host galaxies, and in turn, how does that host galaxy affect the activity of the central supermassive black hole? This gets into this grand idea of the co-evolution between a supermassive black hole and the galaxy it lives in. Astronomers find an evolutionary link between the growth of galaxies and the growth of supermassive black holes. This figure to the right depicts the black hole mass on the y-axis and the mass of the central bulge, or the stellar light component, on the x-axis. They find that this evolutionary trend occurs as the central bulge mass increases, so does the mass of the supermassive black hole. And they find that there's a symbiotic growth between the two. However, they don't quite understand the mechanisms by which they grow together. And we set out to try and answer this question by analyzing quasars hosting newborn jets at different periods in cosmic time to try and put a scheme to this evolutionary trend. However, studying radio jets can be tedious still due to the fact that they only emit in the radio wavelengths, so we can only detect them with radio telescopes shown here. These are the radio telescopes shown in the Very Large Array Sky Survey. And another reason why they're a little tedious is they are extremely dynamic. Specifically, with our sample, we compared 2 radio surveys to detect our newborn jets. In the 1990s, the Radio Sky Survey first is picking up no jet emission features in these top 3 black panels. There's nothing there. And then just 2 decades later, which is the blink of an eye in cosmic time, the Very Large Array Sky Survey starts picking up radio jet emission and these pink features here, indicating that these are in fact newborn jets. However, to study those environmental conditions that triggered those radio jets, we had to use a different telescope, specifically the Hubble Space Telescope, for its incredible subarc second resolution. It observes interstellar sources in the near-infrared, optical, and UV wavelengths. These are the wavelengths of stars and galaxies, the component we're trying to analyze. And specifically on the Hubble Space Telescope, not pictured here, we analyzed our sources with the Wide Field Camera 3 near-infrared instrument. It has incredible sensitivity, wide field of view, and a very, and really good at point sampling for our quasar images. So these are the Hubble Space Telescope images of our sample. There are 4 broad-line quasars selected for their newborn jet formations in the last 10 to 20 years. And the top left, you see their names, the J and then some numbers following, that's their name. And the top right, you see this Z variable here. This is called the redshift. The redshift is related to how long the light from these galaxies has traveled to reach us, and we use this as a proxy for distance. So the lower the redshift, the closer the system is to us, and the higher the redshift, the farther away it is. From left to right, in increasing distance, we see also decreasing detail in what we can already see in these host galaxies. In our closer galaxies, we have tidal streams. Oh, the pointer doesn't work. We have tidal streams of stars already visible, and a tidal tail already visible in this one. However, in all of these images, that quasar light component, that big black dot you see, is obscuring most of the host galaxy's morphology that we cannot, that we set out to discover. To do so, we broke up our experimental method into 3 key phases, beginning with phase 1 pre-processing. In the pre-processing phase, we modeled the point spread function, which is the response of the instrument on the Hubble Space Telescope to an extremely bright point source, such as an unsaturated star or a quasar for our sample. We then implemented that in addition to our background root mean square noise estimation into our images and configured them to prepare for phase 2. But let's go through phase 1 first. We began with the raw data image from the Hubble Space Telescope and its field of view in its entirety. In the blue box here, you can see the target is highlighted, which is our quasar and its host galaxy. And these two smaller boxes here are these candidate point spread functions, which we used unsaturated stars in the image field of view to find. So highlighted in green and orange are the two best candidate point spread functions from this image. There's 3 main forms of criteria we use to determine this. The first of which is a clearly structured wing component that you can see in the 2 of these. And then the second is one point source. That pretty much rules out all of these with more than one point source that's contaminating that point spread function. And last, a full width half maximum value that is similar to that, if not a little bit more than the quasar's full width half maximum brightness value to ensure that we would successfully subtract its light. We verified our point spread functions with scaled surface brightness plots. So on the y-axis you have a scaled surface brightness, and the x-axis is the pixel count, and it just shows how this brightness is changing as a function of the central pixel of the point source and outwards. Next, we configured our images for modeling. We started off by making a segmentation image of the Hubble Space Telescope field of view image itself. A segmentation image is going to detect any emission features in the image itself and create outlines for them so we can easily distinguish between any sources and their emitting features. We did so in order to separate our host galaxy from any contaminating or surrounding sources. So our host galaxy is going to be 0, and all those other ones that we didn't want to model and were contaminating our light of the host galaxy, we masked them in this second image here. So they're covered up and we're only looking at the host galaxy we wanted to analyze. And lastly, in this third image here, we implemented those masks and that background root mean square noise and highlighted on what we are in fact going to analyze, the point source or the quasar in pink and the galaxy component in green. With that prepared, we can move on to phase 2 and perform quasar host galaxy decomposition, where we separate the light of the quasar from the light of the host galaxy it was obscuring. We did so with 3 key Python tools listed here: GalLight, Astronomy, and GalFit. Pictured here is a conceptual overview of quasar host galaxy decomposition. We began with the image of the quasar superimposed on the host galaxy itself, and we subtracted the point spread function from phase 1, convolved with a model of what we estimated the host galaxy would look like. A successful subtraction and modeling of those 2 resulted in this exciting residual image that shows the underlying host galaxy morphology. We can already see in a comparison of just these 2 images here that this revealed spiral arms in one of the quasar's host galaxy in our sample. However, to get to this very nice result, we had to do some robust modeling with the Search profile, which I'll elaborate on next. Here's just a condensed overview of the Search radial profile. The Search radial profile is a function of how the intensity or brightness of light in a galaxy is distributed, moving outward from the center of that galaxy. And this equation shows intensity as a function of several variables, but I just want to focus on this very important n variable here we call the shape parameter. The figure to the right depicts that as we change n, the intensity or brightness of the light in the galaxy also changes as a function of radius. In physical means, a lower n value corresponds to a disk or spiral galaxy, and a higher n value corresponds to a bulge-dominant and centrally condensed light in a galaxy. And upon a successful modeling and subtraction of the quasar, we are left with some exciting morphological results. The leftmost panel here shows just the Hubble Space Telescope image. The middle panel shows the Search model of the galaxy we made, and then the rightmost panel is that residual image of that host galaxy's morphology lying underneath that light from the quasar. We can see in J0950 that this system is undergoing a merging event with other nearby systems that have pulled parts of this galaxy and caused tidal streams of stars around it, and also a prominent dust lane at the center here. That dust lane is indicating to us that, in fact, there is inspiraling dust and gas towards that central supermassive black hole to trigger those newborn radio jets. Here, for J0742, in this residual image, a very different result came through of a spiral structure galaxy with a prominent tidal tail caused by this little feature here, which is an orbiting satellite companion galaxy that caused disturbances within J0742 and triggered those newborn radio jets. For these sources, they were more distant from us at a higher redshift, and therefore that caused their stellar light components to be more faint than our more nearby sources. This limited our resolution. We couldn't clearly see any clear signs of mergers or interacting systems. However, we couldn't entirely rule that possibility out. So this was observationally limited. However, in phase 3, we still could successfully analyze these residual results for different components of the galaxy. So in phase 3, we analyzed those residual host galaxy results with photometry and modeled their light components with spectral energy distributions to ultimately quantize the mass of their host galaxies. We began by extracting the observed brightness of the galaxy in these panels here. The quasar light is in this top panel, but more importantly, this galaxy light right here is in this bottom right panel. We wanted to model that brightness using a spectral energy distribution, which is essentially a model of how the brightness is affected by the wavelength it is emitting from. Specifically for galaxies, a spectral energy distribution is a model of the total combined light of all the stars in that galaxy. We took that total combined light model and its resulting brightness value and fit it to a flux mass scaling relation, pictured here in the figure to the right. The y-axis depicts the brightness, the x-axis depicts the bulge mass component, and we see each dot is a different galaxy, each color is a different galaxy type, and overall we see this trend of as mass increases, so does the brightness of that galaxy. Our mass results followed this trend. Our brightest galaxy, J0742, was our most massive. It is almost 10 to the 12th times the mass of our sun. For reference, the Milky Way galaxy, the one that we live in, is only 10 to the 10th times the mass of the sun. Our least bright galaxy, J2109, is our least massive at 10 to the 10th times the mass of the sun, but stand by because there's a reason for that. We fit our sample to the Herring-Rix mass scaling relation and found that generally it followed the trend of this linear blue line, which is that scaling relation. Our y-axis depicts the mass of the supermassive black hole, and the x-axis depicts the mass of that central bulge. Our one exception, like I said before, J2109, it has that extreme distance that affected its stellar light component, making it extremely faint for us to detect. So it does appear as if that supermassive black hole mass is overmassive compared to the stellar light or the mass of the bulge component, but we can also conclude, though, that it could be a possibility that this supermassive black hole did in fact start out with an initial mass more massive than other supermassive black holes, or it evolved more rapidly than its host galaxy. Interestingly, though, our two merging and interacting systems, J0950 and J0742, lie below this scaling relation line, which indicates that they have merger-driven evolution within their host galaxies. Their interactions with external systems created a burst of star formation, leading to their host galaxy mass components being a little bit overmassive than their supermassive black hole components. And just here is our fit of our sample in the yellow stars here to the Herring-Rix relation in their paper here. Still following the general trend with that one exception of J2109. However, we wanted to look more into the history of one of the quasars in our sample, J0742, and to try and quantify that timeline I spoke about earlier. We used LOFAR, which detects low-frequency radio waves in space, and found that J0742 actually has remnants of old radio jets that have faded away and are barely detectable. The presence of these faded radio jets, in addition to the presence of newborn radio jets, indicates to us that radio jets are not just a one-time event in a galaxy's lifetime, they could be part of a cyclical event. We believe in this cycle, it begins with a galactic interaction that takes 10 million to 100 million years, which is similar to that one of the companion galaxy, triggering the newborn jets in J0742. Then, after about 100,000 years, radio jets begin to form. And then there's going to be another time delay where these jets mature, expand, and fade away if that supermassive black hole runs out of fuel after about 10 million years, like we saw in J0742. And if there is another galactic interaction, then this cycle is kickstarted again and begins anew. In summary, we found half of our sample of quasars with newborn radio jets are undergoing merging activity or external interactions with other galaxies. Our higher redshift or more distant sources show no clear signs of interactions with nearby systems due to either limited observations, but we can't exactly rule out that merger possibility. Besides that, we found success in our approach to decomposing these images of quasars and their light from the stellar light component of their galaxies and revealing what was once unseen. We found a significant fraction of our sample had mergers, and we found that fit with our overall understanding of this symbiotic relationship between black holes and their host galaxies. However, in the slim chance that these galaxies can interact with another one, they can stray from this evolutionary trend and undergo significant changes. So, this explains our understanding of like a coevolutionary relationship between a supermassive black hole, its central bulge component, and how these can, in fact, stray from this evolutionary trend. And that brings us back to those two key questions of how do galaxies evolve and where do we come from? Well, we didn't quite completely answer those questions, but we did gain significant progress in answering them, where we found radio jets, their supermassive black holes, and their host galaxies can have varying relationships and have very different stories in this evolutionary trend. And the future of this study lies with analyzing quasars with newborn jets with deeper and higher resolution imaging, hopefully with the James Webb Space Telescope. And we want to apply this methodology to an even larger sample of quasars with newborn jets found by Nyland et al. In 2020. And I just want to take a moment and wrap up by thanking my advisors, Dr. Christina Nyland, Professor Christopher Morgan, Professor Dana Anderson, and collaborators that provided invaluable insight into this research as well, Dr. Mark Lacey and Dr. Il-Sang Yoon from NRAO. And with that, thank you all, and I'll take any questions. Yes. Not quite instant. We're seeing this light as it's traveled over billions of years to reach us here on Earth. But going back to like comparing our cycle, it could have taken those jets that we detected in 20 years, still that 100,000 years to be fueled and form. We're just seeing from our perspective a difference, a quick difference here. But it could have taken from the in-fuel initially to this emission that like formation of 1,000 years. That makes sense. However, I think we do need to study this sample more and like a broader sample in order to like actually make conclusions about that. Yes. As in like the active galactic nucleus itself, or it's like host galaxy as well? Yeah. Well, an interesting thought is there was this period of increased active galactic nucleus activity in higher redshifts. And then as we get closer to our own and present day, like even within our own galaxy, our supermassive black hole at our center isn't an active galactic nuclei. So we have very different stories for each of these. Some of these galaxies can have an evolutionary trend of just within its host galaxy itself, while in that slim chance of an interaction, these galaxies can come together. We won't be able to see it, but in billions of years, our own galaxy will interact with the Andromeda galaxy. And this is actually a simulation of what that may look like. And that could kickstart and have their supermassive black holes merge together and become an active galactic nucleus and exhibit those radio jets. So you're asking just a timeline of merging events and when okay, yeah. So mergers happen on a way, way larger time scale than a radio jet, and its triggering happens. Mergers happen from 10 million to 100 million years. So if we look at like our residual results here of J0950, for example, so this is still like from our perspective, it's undergoing this. And it probably has been undergoing that merging event for that time frame I gave you, and only just within a fraction of that merging event have these newborn radio jets come through. I think it's due to like a disparity of when that's kickstarted and then how long it takes that dust to reach that central supermassive black hole. Any other questions? Thank you.